Okay, so let's define oscillatory integrals. So we will define I of lambda equal to integral AB EI lambda phi of x fx dx. Okay, where phi is a smooth real function and f is a smooth complex function. So we would like to know what is the asymptotic behavior of I of lambda, okay, as lambda goes to infinity. Okay, okay, so a proposition, okay, let f see infinity in the interval AB, okay, and phi prime x is not equal to 0 for any x in interval, then I of lambda is equal integral AB EI lambda phi x fx dx equal big O lambda minus k. Okay, this is as lambda goes to infinity. This is for k positive integer. Okay. Okay, so you can also say that the absolute value of the integral is less than equal with a constant of 1 over lambda k as lambda goes to infinity. Okay, so this is an equality that may have a constant, but it represents the same thing. Okay, so let's try to prove this. Okay, so let's suppose first k equal to 1, then we will see what happens with the other cases. Okay, so recall that phi prime of x is different from 0, and we can write this in the following identity: 1 over I lambda phi prime dx ei lambda phi x is equal to ei lambda phi x. Okay, so when one derive this, we obtain the same thing. It cancels with this. Okay, so going back to the integral, we can integrate in parts by parts the following way. So we get a b integral ei lambda phi of x, okay, multiplied by f of x dx. Okay, so let's use this identity now. Integral of ab 1 over I lambda phi prime dx ei lambda phi of x, okay, parenthesis fx dx. Okay, so if we integrate by parts, we will obtain a minus integral ab dx fx I lambda phi prime ei lambda phi dx. Okay, so if we take absolute value, we will obtain I of lambda 1 over lambda integral ab absolute value d dx. Okay, f of x phi prime of x. I didn't put the x, but it's always phi prime of x and absolute value dx. Okay. Okay, so one can prove that this integral is a well, not this integral, but what is inside the integral is in L1, so that this is a constant that depends on f psi and phi. Okay, so then we will have that the absolute value of phi is less than or equal than 1 over lambda. Okay, okay, and we will have a constant there. Okay. Okay, so that was for k equals to 1, but one can do the same thing number k of times. So, for example, if we define the operator L of f 1 over I lambda phi prime df dx, okay, and we can have a L t that would be the adjoint of L. It will be equal to minus d dx f I lambda phi prime. Okay, this will be the adjoint of L, and Lk of ei lambda phi will be equal to ei lambda phi. Okay, it's not going to be so different. That's what we did with k equals 1. So if we make the same that we did before, we'll have ei lambda phi f dx equals ab. Now we'll have lk. Okay, because of that, ei lambda phi f dx. Okay, and now we can make integration by parts, but now k times we'll obtain minus 1 k ab ei lambda phi, and now we'll have the adjoint lt k times f dx. Okay, so as it happened in the case of k equals 1, we will have that absolute value of I lambda will be less and equal than 1 over lambda k, and then we will have a an integral that will depend on L. Okay, well, we can write it explicitly like this: dk fx phi prime x okay, so this will be in parentheses, and this should be an absolute value and the x. Okay, and again this integral is going to be a numerical constant depending on f. Oh, let's write it like this: c that depends of f of phi, and in this case of k. Okay. Um, so this will give us the result that we are expecting.